Okay, so let's get started. It's nice to hear that you guys are making progress on your projects. And so again, if you have any questions, shoot me an email. Like I know, I mean, in my version, I did make a class, and you can actually, call the ODE solvers from within a class. So if you have problems, just shoot me an email, and we'll work something out. Okay, but in class, what we are working on is basically deriving the fundamental flame structure, or the fundamental relationship of a propellant flame, or of a steady propagating propellant flame, that the burning rate is equal to some coefficient times pressure raised to some exponent. And we were doing that by actually looking at three different control volumes. One, we looked at a control volume for the condensed phase. Then that got us then that basically got us the temperature gradient at the condensed phase side of the gas condensed phase interface. Then we applied an interfacial energy balance to relate the condensed phase heat flux to the gas phase heat flux. And then now we are using that gas phase. Now we are actually integrating the gas phase flame structure. And what we're going to find for that is a relationship for the gas phase heat flux. And so now basically what we're doing here is we are finding the structure of the flame in the gas, the structure of the temperature, or the flame, if you will, in the condensed phase, and we are using an interfacial energy balance to basically connect those two. And if they are not properly connected, that is, there is an imbalance, then that means then that basically means we have an incorrect flame structure, and we need to guess again. Okay, but the way we are doing it here with all the assumptions, there is no guesswork involved. But in general, there is some guesswork involved, or you're solving, or you turn it into solving a very nonlinear equation. Okay, so we worked with the gas phase, or the condensed phase side, made a litany of assumptions, and found out this relationship. Then we also integrated the temperature profile in the condensed phase side, and then realized that the amount of thermal energy stored inside of the condensed phase decreases with increasing pressure, and that has a consequence on the effect of pressure, which I'll discuss sometime next week. Okay, then this a little smaller. Then now we are working with the gas phase, or then we work with the interface. And with the interface, we jumped from the condensed phase heat flux over here, and we basically applied our conditions. And now we know that in terms of the interfacial, heat of reaction due to either vaporization or an endothermic pyrolysis reaction, or even exothermic pyrolysis reaction, we can now say we use the interfacial jump conditions to jump the heat flux from the condensed phase side to the gas phase side. So now we are working with the gas phase side to basically find a relationship for this and close our relationship for RB, and then we can solve for the burning rate. So we made a whole bunch of assumptions. We neglected the dark zone. We assumed constant properties. We're assuming constant pressure. We're assuming it's steady, and we're assuming that the chemical reactions themselves are uniformly distributed in a very thin reaction zone between some Xi and Xf. Okay, and so we then work with the temperature form of the governing equation, expanded out the terms, the substantial derivatives, and the divergence operators in 1D. And then we work with these sort of nasty sums. And because our equation of state, we are assuming a very simple equation of state, these become extremely simple. That is, the diffusion energy flux, or the mass diffusion energy flux, is 0. And you can show that the sum that the rate of that the sum of the mass rates of production of all the species times their enthalpy is equal to just the mass consumption rate or the mass production rate of the reactants times the enthalpy of a mass-based enthalpy of formation of the reactants. And then what we can do is we can call this, since the mass production rate of the reactants is always less than 0, I'm just going to call this minus omega dot g, where omega dot g is a positive number. You could think of it as the mass production rate of the products times q dot g. Okay, so are there any questions for here? This is where we ended off. Okay, so now we got all these relationships, and now we're going to start stuffing them in to our sort of master energy equation. Okay, so we have this equation here. We showed that dt dx, or dt dt, I should say, is equal to the gas phase velocity times dt dx. The heat conduction term just turns into this, and I'll leave it in this form for the time being, because actually what it may be tempting to basically yank this out, but we are looking for just this term right here. Okay, and then we neglected the Dufour effect. We are neglecting any shear stress effects. We are operating at constant pressure, and we showed that this term goes away, and this term here is negative negative omega dot g times the heat of reaction. Okay, so then simplifying and making these substitutions, we can show that basically rho g Cp times U dt dx, or the flow of enthalpy, is equal to the divergence of the conduction heat flux plus the gas phase reaction rate times the heat of reaction. Okay. So then we're going to work with this. This is constant, so I'm going to divide both sides by the thermal conductivity. And then we wind up doing that, we wind up with this expression here. And now, again, we aren't really after the temperature profile itself, but what we are really after, as I've said before, what we are really after is this temperature gradient right here. And so basically, and then basically we are going to integrate the gas, we're going to integrate that gas phase energy equation using our assumptions, and we're going to basically substitute that that result into here. Okay, so really all we're after is the temperature gradient itself. So that's what I'm going to do. So I'm going to define z is equal to dt dx. Then if I substitute z in, we have dz dx is equal to rho Cp U over lambda times z plus omega dot g qg. And now this here is a fairly straightforward ODE to integrate. This may look non-constant, but it is constant because, you know, because even though rho is not constant, and U is not constant, but rho U is constant. And since we're assuming constant properties, so the Cp is constant and the thermal conductivity is also constant, this entire thing, which is just rho times U times Cp over lambda, is also constant. Okay, and so this here is just nothing but a constant coefficient inhomogeneous but separable differential equation. Okay, and so we can integrate it, and note that at z equal to 0, that is dt dx, or that is the temperature gradient at the interface. And then at z equals infinity, we should wind up with that z is equal to 0, meaning that there is no slope. And so this is just a first order ordinary differential equation. So we do need to be a little bit careful to ensure that that's the case. But other than that, this is a fairly straightforward ODE to integrate. And so if we integrate, and then solve for the temperature gradient at the interface, and multiply that by the thermal conductivity, we wind up with this expression right here. So we have just the heat of reaction, which is just a constant, times the integral from 0 to infinity, and we are integrating from x equals 0 to 0 plus to add to x equals infinity. Okay, because of the interface, when you say you are integrating, you do need to be careful of whether, and if you start at the interface, you need to be careful of whether it's 0 plus or 0 minus, because that means you're starting from two completely different places. So we are just starting, so we are only working on the gas phase side, and so we are integrating from 0 plus to plus infinity. Okay, so anyways, we integrate this, the ODE, and we get this expression right here. Okay, so far we can't do a whole lot with this, because in general, omega dot G, or the gas phase reaction rate, is a very complex function. In reality, it would probably look something like this. So here's the flame structure right here, and the reaction rate would probably look something like that. And so this is in general a horrible, nasty equation to integrate. So instead, we're going to invoke our assumption that instead of this really nasty function here, we're going to approximate this peaky profile by assuming, by basically turning it into a step function. So instead of the thing that I had drawn, this, we are going to approximate this curve to be like this. Okay. And basically what this allows us to do is now omega dot G is not this really nasty function here, which we don't know, but we've assumed it to be piecewise constant. And if it's piecewise, and in most places it's 0. And then if omega dot G is 0, this is a very easy function to integrate. I would hope a freshman undergrad would be able to integrate that one. But so now what this means is that if we're assuming that this that we are going to make this approximation to the gas phase reaction rate as a function of distance, our functional form for that is just basically this here. It's 0 if it is less than x sub I. This here is xi, and this here is xf. And it is some averaged reaction rate if we are between these two limits. That's red. I'll make it blue. It is some average reaction rate if we are between these two limits, and it is 0 after we've consumed all of the reactants. Okay, where again omega dot G bar is an averaged reaction rate. Okay, it's just a definition, but the fact that it is piecewise constant and all this stuff here is constant, this now becomes a very straightforward integral to straightforward integration to perform. Okay, so we can now evaluate that. So we basically work out this integral here, and then do the integral. We wind up with this expression here, and then it just winds up of being this basically this integration constant multiplied by e to the minus rho u Cp over lambda times the starting point of the chemical reactions times the exponential of the same thing times the final point of the point where the chemical reactions stop. Okay, and then so this is a more generalized expression, and we're going to make a further assumption, because in reality, those pyrolysis species that come off the surface of the propellant, so if we have our propellant here, those pyrolysis species are extremely reactive. And if they are extremely reactive, they start reacting right away. And so in general, for simplicity, and it's also somewhat accurate, we can assume that xi is equal to 0. So we're going to assume that this is equal to 0 because it makes the algebra a bit easy, and it is somewhat physically accurate. Okay, just because the pyrolysis species that come off of the surface of a burning propellant are very reactive. If they weren't very reactive, a propellant would not be able to burn stably in the first place. Okay, so they have to be very reactive. Okay, and so then if xi is 0, this here just becomes 1. And so if we assume that xi is 0, our expression for the gas phase thermal conductivity becomes this. Okay, now we're going to make further assumptions. And just note, yeah?
Can I ask a quick question about the assumption we just made?
Yeah.
So if we had included a dark zone into this, would we set xi equal to whatever that thickness of the dark zone was?
No, because what we're after is a temperature gradient at the interface. So the reason that we neglected the dark zone is because you could either view it as we are completely neglecting it, or the dark zone is way over here. Because again, because what is controlling the propellant burning rate is the gas phase heat flux, basically impacting the surface, and that is really controlled by and basically that is controlled by the fizz layer. Okay, and so you could either view it as we are neglecting it completely, and not all propellants at all conditions have a dark zone, or we are just really looking at this portion basically this portion of the flame structure right here. Okay, either way it works.
Okay.
Does that make sense?
Yeah, I thought the dark zone was before the reaction zone, so I had that mixed up.
Well, there are really two reaction zones. There is a reaction zone in the fizz layer, and there's a second reaction zone in the flame zone, if that makes sense.
Okay, gotcha. Thank you.
Okay, yeah, it's sort of confusing, but you sort of need to view this as kind of, in general, the gas phase flame structure, even for a homogeneous propellant, is sort of a double flame. Is that there'd be a flame following another flame. And so the first flame would be the chemical reaction in the fizz layer, and the second flame would be the exothermic reaction of the dark zone species. Okay. Does that make sense?
Yeah, thank you.
Okay, but either way, we are neglecting the dark zone. And so anyways, so we wound up with this expression here. And also, this isn't an exact analysis by far, because we've made a whole bunch of assumptions. So all we are after is basically, can this really simplified analysis reproduce our burning rate law? That's all we are after. And so this is just a rough order of magnitude analysis, is basically all this is. Okay, so now we have this quantity Cp, or rho Cp over lambda everywhere. And that's just the thermal, and then you guys may recall from heat transfer, that's just the inverse of the thermal diffusivity. Okay, and then for a propellant, the thermal diffusivity is on the order of 10 to the minus 5 to 10 to the minus 4 meters squared per second. So it's pretty darn small. Propellants, especially a composite propellant, the binder is HTPB, which is basically rubber. And so basically the insulating qualities of a propellant, without any little metal wires and things embedded into it, is basically that of a rubber, which is a very good insulator. And so the thermal conductivity and the thermal diffusivity of a propellant tend to be quite low. And so that's also why in a lot of rockets, behind the propellant itself, you have the propellant here, and then the combustion chamber, is that there usually is not very much insulation. If basically this is the outer wall of the rocket, and this here is the propellant, is that there is not that much insulation normally between the propellant grain and the outer casing of the rocket in a region where there is propellant. And the reason for that is quite simple, is the fact that for the most part, the propellant is acting as its own insulator. You do have to be careful if there are regions where the propellant burns completely, and then in those regions, you are going to have to basically add some insulation. But the propellant normally acts as its own insulator, and so you don't need. So in regions that are covered by propellant during the burn of a rocket, you don't need a lot of. You don't need to get carried away with insulating the back end of it. In the rocket test in Ken Poe's lab, essentially what they used to insulate the rockets was just the canister, just a phenolic canister that the grains were cast in the first place. They just basically slid those in, and that worked well enough. And that's just basically thin, compressed, hardened paper is basically what that was. And so that's just a little sort of factoid that you may or may not be interested in. But anyways, so that was a tangent. But the thermal diffusivity of propellants is quite low. Then we are taking U times X, which is nothing more than a sort of representative flow time, and we are dividing it by thermal diffusivity. And since the thermal diffusivity is small, we can assume, it's kind of shaky, but we can assume that this quantity here, U times X, or a sort of U times X over the thermal diffusivity is a pretty darn big number. Okay, because basically 1 over the thermal diffusivity is already a huge number, and XF may be on the order of a millimeter or a few hundred micrometers, but UG is also going to be on the order of maybe 10 meters per second. So and so basically these two will basically cancel out in terms of their order of magnitude, and then that will be of order 10 to maybe 100 sometimes. Okay, and so basically this number will be fairly large. And then after you put this fairly large number in this exponential, this is actually going to be a very small number. And so then e to the minus, if you make that assumption, e to the minus UGXF over alpha G is going to be a very small number. And so this term here goes away. And then finally, we've gotten rid of all of the nasty terms, and we are only left with the conduction heat flux on the gas phase side is just equal to this right here, because this is 1 and this term is now 0. Okay, so are there any questions with that? Okay, and so recall, we still need to work with this. So I already showed this, but I think it sort of bears repeating. Since we're assuming steady or even if we're not assuming steady state we're assuming steady state operating conditions, and so that demands that rho g UG is equal to 0 everywhere. I mean, is a constant, or is a constant everywhere, not equal to 0 everywhere, but it's a constant. And basically, you could do a control volume at any point, even across the surface. And if it's across the surface, you can show that basically the density of the propellant times the burning rate is equal to the gas phase density times the blowing velocity of the gas coming off the surface. Okay, so we know then that basically, and this basically means that the mass flux going in from the condensed phase side is equal to the mass flux going out of the gas phase side. And I could draw this control volume anywhere in the gas or propellant, and the same would be true. Okay, so what this means then is that rho P RB is equal to rho G UG, and I can take this and replace it with basically rho P RB. So finally, we have related the gas phase conduction heat flux. We have related it to the burning rate times a bunch of crazy constants. Okay. And so, and then if you really wanted to, you could integrate the gas phase temperature profile. I'm not going to do that because that starts getting fairly for this analysis, that starts getting fairly complicated. But it would look something like this if you were to do it. It'd have a sort of exponentially sort of growth, and then basically asymptote to some flame temperature. Okay.
So
But anyways,
does the thermal conductivity cancel out here then? The lambda, it's on both sides of the equation. So is our temperature profile not a function of our thermal conductivity?
oh no, if you integrate the temperature profile, yes, it is.
Okay.
But this is just saying that this is just basically we're just substituting this into here. Okay.
Okay.
Yeah, that's just saying that the conduction heat flux at the surface is equal to this. I'm just saying if you integrated the master differential equation a second time, you could find the temperature as a function of distance if you really wanted to. But that's a fairly nasty exercise in that, and because we made so many assumptions, and a good half of them on fairly shaky grounds, I don't think it's worth going through that. But I'm just saying that you would get some temperature profile that would look something like that, and then that would be mated to the condensed phase side, and that temperature profile would look something like that. Okay. So anyways, now we have completed analysis in the condensed phase, gas phase, and the interface. And recall that we previously had that lambda G dt dx on the gas phase side of the interface is equal to this expression here, which was derived using the condensed phase analysis and the interfacial energy balance. And then now we can combine with our result over here and say that this expression here is equal to this expression over here. Okay. And so now we have RB here and RB there, and we solve for the burning rate. And we wind up with this expression right here. So now you guys might be thinking, WTF, we computed the burning rate and it looks absolutely nothing like AP to the n. Looks absolutely nothing like AP to the n. So so you guys may be worried that I wasted your time. No, I did not. Or maybe I did, but at least not in this context. So we have to recall that what is a function of pressure here and what isn't a function of pressure here. The propellant density is not a function of pressure, or if it is a function of pressure, it's a very weak function of pressure. Again, we're not at crazy detonation-like pressures where the solid material also becomes extremely compressible. We are at much lower pressures. The thermal conductivity isn't really a function of pressure. Specific heat of the gas is not a function of pressure. Again, unless you start getting to crazy high conditions or close to some sort of critical point. And in some propellants, that does become an issue when you're burning them, say for a gun propellant where the pressure can get to 100,000 psi. You do have to worry about that stuff, but nobody ever really accounts for it properly. Just because there isn't enough known about the parameters of the propellant species to even do a formal like supercritical combustion a model for them in the first place. But anyways, this here is constant. So basically everything here, except for maybe the surface temperature, but we're going to assume that's constant anyways, except for the surface temperature and the average reaction rate is basically constant. But again, we will assume that the surface temperature is a constant. That is actually absolutely not true, but we will assume it's constant anyways. Now, so where does the pressure dependence come in here? Because nothing here is explicitly a function of pressure, with the exception of the gas phase reaction rate. So recall that we discussed way back in the day. It feels like 47 years ago, but when we were discussing the chemical reaction rate, we basically discussed that the reaction rate scales with increasing pressure based on a power law where the exponent is the overall order of the reaction. So if I have a reaction like this, let's see, H2 plus O goes to H2O, that would be a second order reaction, and how fast that chemical reaction occurs would be proportional to the pressure squared. If I had H2 plus 1/2 O2 going to H2O, the overall reaction order would be the sum of the stoichiometric coefficients, so 1 plus 1/2, and so the overall reaction reorder for this global reaction right here would be 1/2. And so basically the gas phase reaction rate would then scale with pressure raised to the 1.5 power, etc. So basically M is equal to the sum of the stoichiometric coefficients. Okay, and then for a global reaction, it would be the sum of all the powers on the global reaction rate. But anyways, so basically M here is a measure of the pressure raised to the overall reaction order. Okay, so now I'm going to work with this, and armed with that sort of tidbit of knowledge, I'm going to factor out this omega dot G to basically separate it out. And so here we have the square root of everything else times the square root of the average gas phase reaction rate. This here is essentially constant, and this here is not going to change that much, so it's kind of almost constant, but really isn't. But anyways, we will treat it as a constant. You'd have to do a much more detailed analysis to get an estimate of the surface temperature. But now we can use our argument here based on that the gas phase reaction rate scales with pressure raised, or with basically power with pressure raised to the overall reaction order. And then if you take the square root, it just becomes 1/2. So then this constant, I'm just going to call this constant A. So then now we have the burning rate is equal to our constant A times pressure raised to the overall reaction order of the gas phase divided by 2. Okay, so M over 2 is just another exponent, and I'm going to call that N. So then we have done all that work, and we've shown that the burning rate is equal to a coefficient times pressure raised to some exponent, and this is basically Saint Robert's law that he determined empirically. Okay, so basically what this analysis basically shows us is that, yes, if you get the fundamental physics right, that basically you need to match the gas phase flame to the heat conduction and the energy change inside of the, or you need to match the gas phase flame structure to compute the gas phase conduction heat flux into the propellant, and that needs to be balanced with the overall energy change of the condensed phase propellant by basically raising it from the initial temperature to whatever the surface temperature is of the propellant. And so basically what this means is that to find the burning rate of a propellant, it's not a simple, straightforward problem like it was for a Chapman-Jouguet detonation or a Chapman-Jouguet flame. Instead, you actually need to consider the structure of the flame in order to compute the burning rate. And in general, we made a whole bunch of assumptions so that we could basically solve for it algebraically. But in reality, what you have to do is you need to guess RB, and then compute the flame structure of the gas phase side, and then perform a matching energy balance. If the interfacial energy balance criteria is met, that is your assumed burning rate matches is basically mated, or the gas phase flame using your assumed burning rate is mated to the condensed phase region of the propellant properly. You are done. You have your burning rate. If not, you need to guess again. Okay, but we made all those crazy assumptions so that we could basically solve for it in this step right here in a very straightforward fashion. And a lot of the assumptions that we made are on pretty shaky grounds. But nonetheless, if you refine this analysis, and you solve for the surface temperature, and you do also all sorts of other things, what you basically wind up with is a much more complicated formula here that is still not accurate, that you still can't use it to predict anything with any reasonable accuracy. But at the end of the day, so you go through all that extra analysis, all that extra awful algebra, solving the eigenvalue problem to find the burning rate, and at the end of the day, its only use is it provides a little bit more physical intuition here, and it still just basically tells you that the RB is AP to the N. Okay, and basically it's basically telling us here too is that there is also a sort of small temperature effect, that the more we have to heat up the more we have to heat up the propellant to reach the surface temperature, the slower it's going to go. So there is a temperature effect that is kind of baked into this expression. And then also, if the surface reactions are like endothermic, like a vaporizing propellant such as nitromethane, then QS will be negative, and that will also slow down the burning of the propellant. If the pyrolysis reactions are exothermic, that is, we are releasing energy right on the surface, that will have a large impact on increasing the burning rate, because we are depositing thermal energy, or basically sensible thermal energy, directly right onto the surface, where it can feed, where it can basically directly input energy into the condensed phase propellant. Okay, so even though this analysis we made a lot of really hand-wavy assumptions, it is still really useful in terms of the basic physics and the basic understanding. Okay, so are there any questions on this?
Professor, what's the significance of setting m over 2 equal to n? Like, if they're both just exponents, and also wouldn't m over 2 tell us the overall reaction order?
Yes,
But N is just like some constant.
yes.
We're not.
The only reason I did that is because traditionally propellant burning rates are cast in this form here. And so basically it is tradition to actually just call P raised to the M over 2 as just P to the nth power. And that's basically tradition. Basically don't ask me why. It just is.
Okay.
And then, yeah, and then basically, if your propellant burning rate has, if it's proportional to P to the 0.7, that means that at least at that pressure condition, the average gas phase reaction has an overall reaction order of say 1.4. And it does mean that.
Okay. So it's known that N would be M over 2 in
Yes.
these kind. Okay. Okay.
Yeah, and again, there are a lot of other physical effects that can also affect the burning rate constant. So that's not, so it is a bit hand wavy, but even for real propellants, this burning rate exponent is a strong indication of the overall reaction order of the gas phase side. Okay, but there are other things that can affect it too, such as if you put a catalyst that can add some pressure sensitivity to the reactions in the condensed phase side of the propellant. So there are other things that can influence that, but at least based on the assumptions that we made, that all the reactions are occurring either on the surface or in the gas phase, then yes, this is then it is an indication of the burning rate exponent is an indication of the overall reaction order. Okay. Any other questions?
You have a question about the mass rate of production. We said it's proportional to pressure to the M, right?
Yeah.
Do we need to add in, or couldn't we find the constant that makes that equal and add that into, to changing our original A constant?
You mean if you really wanted to compute it?
Yeah, could we find that it's equal to some constant time pressure to the M, and then bring that constant into our A value to give us a better result?
Not really, because we're already hosed with all the assumptions that we've sort of made. Because again, in the regime that we are in, is omega dot G really will be equal to just say we'll just look at basically this one right here would be equal to the molecular weight times H2 times O2 to the 1/2 times A, and I'm running out of room, times E to the minus EA over RUT. And so this is what it really is. And the pressure dependence comes into here. And there's also a strong temperature dependence. So basically we are ignoring all of these sort of crazy details that are involved with finding the rate of the overall burning rate of the gas phase site, and just saying that there is a pressure dependence, and that pressure dependence comes from the sort of concentrations, and that's basically where this M comes from, and we are only concerned with that part. But if you wanted to use a more precise theory, and then basically do that, then basically, yeah, then you could insert that and put it into here, but then you would also need to figure out what to do with the Arrhenius term. And in this class, we are not going to go over that, but essentially, typically you assume either high or low activation energy which then allows you to make some simplifying assumptions there. And hint, it was determined in the theoretical analysis that the activation energy of the pyrolysis species is near zero because they are very reactive species. So then that would allow you to get rid of this term, and then you have constant, and then ideal gas law for this. And then you could in principle do that to make a better approximation, but then you need some sort of averaged temperature, some sort of average mean temperature that you can use to basically approximate these terms using when you relate them to pressure and the ideal gas law. Okay, does that make sense?
Yeah, that does. Thank you.
Okay. Okay, and then so just recall that I'm just going to go over some physical effects here. That for gas phase flames, you can repeat the same analysis. One of the key differences are there's no surface, so QS would be 0. This term would go bye-bye. Basically, this term here just goes to 1. And rho P is now rho G, and that is proportional to pressure. And so what you would wind up with a gas is you wind up that the laminar flame velocity scales with pressure raised to the m-2/2. And so basically you for a gas, you have a completely different scaling of how fast the flame propagates through a reactive gas mixture than it does for a solid propellant. And this extra basically minus 2, that comes from the fact that the gas phase density is a function of pressure, whereas for a solid propellant, it's at most at propellant burning conditions, it's a very weak function of pressure. Okay, and then also what's baked into what's easier to show in the gas phase side, but it's also true for the propellant side, is that the laminar burning velocity for a gas scales with the square root of the thermal diffusivity times a mean reaction rate. And the thermal diffusivity is representative of heat conduction from the high temperature products propagating into the cold reactants. And the reaction rate is representative of heat release due to chemical reaction. So if we have X and T, and we have a propagating laminar flame, the temperature profile will look something like this. And so for gas phase flame, you can divide that into at least 2 regions. You have this region here, which is called a preheat zone. There are no chemical reactions there, but there's still a rise in temperature. And what is rising the temperature in the preheat zone is heat conduction from the high temperature products on the gas phase side. And then you have a reaction zone right here, and that is where there are where there's both heat conduction and rapid chemical reactions. And so Stefan Terns' book has a very nice analysis of this that basically derives this expression. It's a bit easier than the propellant because you don't have to deal with the interface. But what this basically tells us then is that how fast a flame goes is dependent on 2 things, and it's a balance between these 2 things. Is that how fast a flame propagates is dependent on how fast thermal energy can be transferred from the high temperature products to the cold reactants. Because again, because if you have, say, hydrogen air at 300 Kelvin, it's not going to burn. And so something to keep a stable propagating flame, some physical process needs to occur that is causing the temperature of the temperature that is heating up those those cold reactants to the point where they can burn. And that process is heat conduction from the high temperature products to the cold reactants. Okay, but now that heat conduction is removing energy away from the flame zone. So if it removes too much, you start to slow down the chemical reactions. And so this basically means that the faster the chemical reactions are, the faster that heat conduction can basically transfer energy from the products to the reactants, and the faster the flame goes. Okay, and so that's basically means, so but that's sort of physically why the laminar burning velocity for gas is proportional to the thermal diffusivity and the net reaction rate. And I go over this analysis when I teach, when for gases, basically when I teach undergrad combustion. Okay, and so, but there's, even in this really simple result, here are an analysis for a propellant. Even in this simple expression here, that the laminar burning velocity is proportional to the square root of the thermal diffusivity times the reaction rate. There is a lot of physics that are implicitly baked into that expression right there. Okay, and so I will stop there for the day. Do you have any questions?
Can we go back up to the AP to the end, the equation right above that we derived A from?
Mhm.
So if our surface temperature, it jumps up to a really high value, does that mean that our burning rate slows down? Because your TS minus T0 is a bigger number?
Yes, at least according to this analysis. But now I think the way you're asking the question, to you that seems that seems counterintuitive, right?
Right.
Well, the reason that is counterintuitive is because you are sort of conflating surface temperature with surface heat flux. So if you increase the surface heat flux, and we basically neglected that effect, but if you increase the surface heat flux via radiation or a laser, which is radiation, is that if you increase the surface heat flux with radiation, you will in fact increase the burning rate of the propellant, because you are adding more energy into the condensed phase side. And the reason that if you increase the surface temperature, according to this expression here, the burning rate slows down, the basic reason that is that, so if you look at the temperature profile in the condensed phase, there is, if say the surface temperature is basically way down here, the reason the propellant will be predicted to burn faster is because it's going to take a lot less energy that basically needs to be absorbed by the propellant to raise it from its initial temperature to the surface temperature that allows it to stably burn. So there's just less energy that needs to be absorbed by the condensed phase propellant to basically cause it to burn. And if the surface temperature is higher, say up here where I have it drawn, there is a lot more energy that needs to be absorbed by the propellant to cause it to burn stably. Okay, and so basically, that basically, and then the fact that it takes more time to absorb all of that energy, it takes more distance inside of the propellant for it to be absorbed. All of those basically work in slowing the burning rate of the propellant down. Now, what can increase it is if I have an additional heat flux by, say, a laser or something like that, that is adding additional thermal energy to the surface. And then basically what will happen is that will increase the heat flux going into the condensed phase propellant. And yes, that will also increase the surface temperature, because the surface heat flux and the surface temperature are non-linearly coupled. But in general, if you could fix the heat flux and just vary the surface temperature, you would find that effect, like I showed, that is in the expression. Okay, does that make sense?
Yes, it does. Thank you.
Okay, again, a fairly simple expression here, not physically accurate, to produce predictive numbers, but there's still a lot of physics that is baked into this little expression right here. Okay, any other questions? Okay, if not, have a good weekend.
Thanks, Professor. You too.
Thank you, Professor.
You too. Thank you very much.